Welcome back. Welcome back to another lesson of digital physics. I think that sounds kind of cool. I don't know if it really means anything, but today we're going to talk about measuring temperature. You're going to hear a whole lot about a bunch of different types of thermometers. So I hope you're ready for this. Are you ready for this? Da, 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 thermometer. Okay, here we go. Since materials expand in proportion to temperature change, they provide a way of measuring temperature. Galileo used this property of expansion to make his first known thermometer. He called it a thermoscope, and this is a picture of a thermoscope, so if we want to go ahead and point that out, boom, like that. And it was based on the expansion of air. His thermoscope consisted of a glass tube that had a glass bulb at the end that had air in it. And there was like a liquid at the bottom of the thermoscope. And as the air around the bulb heated up, it forced the air to kind of move and push down the pipe. So they knew that the lower this thing was, the hotter it was. And conversely, when it got colder around the bulb, the air would contract and the fluid level would rise back up. So this was an early way to detect temperature change. But there was a drawback. Not only did it respond to temperature, but it also responded to air pressure. So this was not like an amazingly perfect way to measure temperature. But you guys can see even nowadays that measuring temperature is kind of crucial, whether it's measuring like the outside temperature for what you're about to wear, or even like nowadays measuring temperature to catch fever with this COVID-19 that we have going around here. Like that's an important like task that we all have to kind of be ready to do. So Galileo invented his thermoscope, but it wasn't perfect. And since then, we've come up with a whole bunch of different ways to detect temperature, and we call those objects thermometers. Thermo meaning heat, all right, and meter to measure something, so thermometer. Now, gas thermometers are more accurate, but they are way less convenient. And for a lot of reasons, we definitely need convenience. We need portability. We need not to be attached to a natural gas source at all times. All right, so now we use liquid thermometers, which use liquid sealed in glass tubes under a vacuum. So these are very common thermometers using liquid thermometers instead of gas thermometers, and definitely instead of a thermoscope. Okay, so gas thermometers are accurate, but they're less convenient, and nowadays, 2020, we care very much about convenience. Or maybe if this video is used in the future, whatever year you're watching this, we definitely probably still care about convenience. Liquid thermometers use liquid sealed and okay, we already read that. Okay, cool. Here are some things about liquid thermometers that we have to keep in mind. Number one is they must be calibrated. All right. You remember how when you guys do all of your lab experiments and you never calibrate stuff, you just start measuring things? Why is it so important to calibrate things? Well, you kind of want them to be accurate. If you're going to go through great lengths to be accurate, you might as well be using thermoscopes if you don't even want to be that accurate with things. Right? Am I right? I feel like I'm right. Okay. And also, liquid thermometers must be sensitive enough that a small change in temperature produces a noticeable level change in the liquid. Now, this is pretty important. It's kind of an underrated aspect of thermometers, that if you guys have ever seen like a picture of a standard thermometer, like take this guy for instance. This guy is a thermometer. And with this thermometer, like the classic, the red needle rises up to the top type thermometer, right? It has to be sensitive enough that a small change in temperature, that 1 or 2 or 5 degrees, will give you an actual change. You could actually see that something has changed, whether it goes up, whether it goes up or whether it goes down. All right? We want to make sure that we can actually detect changes in this thermometer. All right, so thermometers are kind of useful, I would say, and we want to make sure that they're useful to us and that we can actually detect these things with the human eye. All right. They should also respond quickly to changes in temperature, because if we care about temperature and what temperature it is outside or what temperature it is in our body when we're talking about illnesses, then they should probably respond quickly. We don't want to have to wait 3 hours later and see, did the temperature change? Because chances are it did, and chances are, like, you're not concerned about the temperature from 3 hours from now. You want to know right then and there. The mass must also be small in relation to the bulk of the object whose temperature is being measured. Like that example of the thermometer that we had earlier, like this one, or maybe one like this one. Maybe this type of thermometer might be useful because it's so small. This is the common type of thermometer, a digital thermometer that you might use to take your own personal temperature. Now, the mass must be small in relation to the bulk of the object whose temperature is being measured. Can you imagine if this thing was like your size, right? It wouldn't be very convenient, wouldn't be that easy to use, and like honestly, it wouldn't be very helpful. So we had to develop more portable thermometers, instead of that big thermoscope with the big glass tube thing carrying that around. Imagine putting that thing under your tongue to try to take your temperature. And we actually have stuff like temporal thermometers that actually are portable too. So we want to kind of keep these in mind just to make sure we're getting the most use out of the materials that we have. The medium, which is just a fancy word to say usually a liquid or the object that something is transferred through, used in a thermometer must be appropriate for the range of temperatures being used. I'm going to go ahead and highlight that word. All right, it must be appropriate for the range of temperatures being used. Now, would it make sense if we had a thermometer that was filled with water? All right, if we had like a glass tube, that's a bad line. All right, if we had like a thermometer that had a glass tube coming across here, terrible, and we filled it with water on the inside. You can't even see that blue. It's a terrible, terrible blue. Let's go with this blue, and it's probably, all right, filled with water. What would the limitations be of a thermometer that is filled with water? What is the highest temperature it could actually read? Well, probably around 32 degrees Fahrenheit. Why? Well, water freezes at 32 degrees Fahrenheit. So water is not an appropriate medium. It's not something that we should put in our thermometers because it would have limitations. All right, once it gets 32 degrees or it goes down to 32 degrees, it kind of freezes there, and you can't go anything lower than that. All right, because 32 degrees would be it. That's why instead we commonly use mercury. It's a very commonly used material whenever we produce liquid thermometers. Since mercury freezes at negative 39 degrees Fahrenheit, or Celsius, my bad, mercury thermostats cannot be used to measure temperatures at or below that point. So because it freezes at this very low temperature, we can't use it for super low temperature situations. But this is very commonly used in most liquid thermometers, because where on earth do we usually get to negative 39 degrees? Thermometric. Let's go ahead and talk about thermometric. A thermometric property of a substance is any measurable property that changes in proportion to a corresponding change in temperature. When temperature changes, the object changes as well. So if you want, you can go ahead and pause it on this screen and you can copy down this note. But we just want to kind of note, see what I did there? The thermometric property of a substance is any measurable property that changes in proportion to a change in temperature. Other temperature measuring instruments, these are just common things that we can kind of note. We're not going to talk too much in depth on these things, but we just kind of want to make note of them. Are resistive temperature detectors, or also called RTDs. There are things called thermocouple junctions. Kind of just make note of that. There are mechanical thermometers, and then there are digital thermometers. Earlier I showed you a picture of a digital thermometer. That's a very commonly used temperature measuring device. All right, let's go ahead and talk about temperature scales. The first one we're going to talk about is Fahrenheit. All right, probably the most familiar temperature scale to people in the United States is the Fahrenheit scale, devised by Daniel Gabriel Fahrenheit. He initially made his 0 point the lowest temperature that he could obtain with a water ice salt solution, and his other fixed point was the normal temperature of the human body. Following a suggestion from Sir Isaac Newton, he set the temperature of the human body as 12 degrees and used this as the upper reference of his temperature. After a series of changes in his methodology, he is eventually settled on 32 degrees being the freezing point of water and 212 degrees being the boiling point of water. He chose these reference points knowing that there's 180 degrees between them, and that meant that the human temperature, instead of being 12 degrees like he initially settled as the line, became 98.6 degrees. Then this dude named Anders Celsius also used the freezing and boiling points of water as reference points for calibrating his own scale. His scale set the freezing point of water at 0 degrees and the boiling point of water at 100 degrees. Now both have their merits. I do agree that setting freezing at 0 makes a lot more sense, and it's easier to remember than 32 degrees. And the boiling point at 100 degrees Celsius makes a lot more sense compared to 212 degrees. But the temperature scale has a lot of varying degrees in between for Celsius, meaning that 1 degree Celsius is a really big change, and having more frequent little lines in between on our scale, that is actually very helpful. So both have their merits, and in America, we're definitely a bunch of Fahrenheit fans. The absolute or Kelvin scale was also developed because well, one, they wanted to know what's the lowest minimum temperature something can actually exist at. And after experimentation with temperature-volume relationship of gases, scientists extrapolated that the minimum possible theoretical temperature is negative 273.15 degrees Celsius. And named after some British physicist dude named Lord Kelvin, suggested in 1854, that this became known as 0 Kelvin, and this became the absolute temp. Now, the absolute 0 is a temperature of matter which there is no thermal energy. It is not achievable in the real world, but it is a theoretical scale that other values are compared to. Now, absolute or Kelvin scale also uses a triple point of water as a reference, but the degree symbol is not used. Compare that to things like degrees Fahrenheit or degrees Celsius. We do not use the degree symbol when we represent Kelvin. You would seem quite foolish if you ever said degrees Kelvin. Don't do that. Don't do that. All right, we also have to be able to convert between Celsius and Kelvin. If we ever wanted to find a temperature in Kelvin, you would take the temperature in Celsius and add 273.15 to it. Or if you ever have want to find the temperature in Celsius, you would just take the Kelvin and subtract. This is what Fahrenheit would look like. And either one of these two works. They both mean the same thing. And you would use this for Celsius to Fahrenheit. Write this last slide down and you're done.